All right, today we're going to be on chapter 23. We're going to be doing distribution of random variables. So we're going to be looking a little bit further into that, and we're going to talk about how to calculate the expectation of a random variable experiment, and how to calculate the expected return from a game, and also use the binomial probability distributions to calculate the probabilities from a binomial experiment. All right, we've talked about a little bit of binomial experiments before, but we're going to be taking a little bit further and putting a little more vocab in. All right, so why don't we start off with maybe something like a little bit of a review, but try out the problems, okay, and pause it and then come back. Okay, so a die is rolled 120 times. On how many occurrences should we expect the result to be 6? So if we have a fair die, then we're going to have 6 different sides, so then 6 should show up 1 out of 6 times. And then if we multiply that by 120 trials, we'll get 20 times we are expecting this to occur. Okay? So then if we roll the 2 different dice and they're rolled 120 times, how many occurrences should we expect the sum to be 6? Okay? Well, there are 5 different ways to get the sum to be 6. All right? And there's 36 different outcomes in rolling 2 different dice. So if we have 5 over 36 multiplied by 120 times, we'll get about 16.6 times we should get the sum to be 6. So a little bit more than halfway between 16 and 17. So almost 17 times we should get 6 as our sum. So the expectation, okay, so we're kind of finding the expectation, what we would expect it to be. So the expectation, there are n number of trials in an experiment, and the event has the probability of p occurring. So our probability on that last one was 1/6 or 5 over 36. Our trials were 120. So they're occurring in the trials, then the number of times that we expect the event to occur is going to be n times p. So that's what we were just doing. So we were finding out the expected number of times this event to occur. We can also talk about the expected outcome from one trial of an experiment. So this wasn't an experiment what we did before. That was what we expected the outcome theoretically. But if we have an experiment, then we can actually find the expected outcome from a random variable experiment, which is going to be x, is the mean result. And we're going to call that mean result mu. All right, in general, the expectation of the random variable x is mu, which is going to equal to the sum of all n trials, okay, the sum of the trials, which is going to be x with its corresponding probability. So the times that I would get, the times I got 1 on my roll, or the times I got 1 on my roll, and with the probability that I actually got rolled in that experiment. The time I got 2 with the probability I got 2, 3. So you get the idea. So it's going to be an expected, and you're going to multiply those together and then add them all up. Okay? So, like this one. So we have a magazine store recorded that the number of magazines purchased by its customers in 1 week. So we have our xi and we have our pi. Okay? So The number of magazines we sold were 2, 1, 2, 3, 4, and 5. Okay, that a customer came in and bought. A 23% of the customers that bought magazines bought just one. Okay, 38% of customers that bought magazines just bought 2. 21% of customers that bought magazines bought 3. 13 bought 4, and 5 bought 5. Okay? So if we want to find out what the mean number of magazines being sold are, we have to multiply our P and our X together, our corresponding values together, and then add them all up. So we're going to have 1 times 0.23 plus 2 times 0.38 plus 3 times 0.21 plus 4 times 0.13 plus 5 times 0.05. Okay? So if you take all those, add them up, we should get to a number about 2.39 magazines. So that is going to be the average number of magazines that a person is going to come in and buy. All right? So we're going to use that same idea a little bit to talk about fair game. So in gambling, we say that the expected gain of a player from each game is the expected return or payout from that game less the amount that is cost, or minus the amount that is cost. Okay? So we have the expected gain, which is equal to our expected yield minus the cost. So, and if that is equal to 0, then it's considered a fair game. So if we look at our problem here, all right? Okay, so we have a spinner, and when that spinner lands on 1, we get $1. And if it lands on 2, we get $2. And if it lands on 3, we get $5. And if it lands on 4, we get $8. Okay? So in this game of chance, when a player spins, a square spinner is labeled 1, 2, 3, or 4. I just showed you the amounts. Okay, so why don't you guys try this problem down here while using our idea or our equation up there. Okay, so the expected return for one spin of a spinner. Okay, so the expected return. Okay, our expected return is going to be our mean, or our mean value of the return. Okay, so a spinner has 4 sides, so everything has a 1/4 chance of getting picked, right, or getting landed on. So if we multiply this out and then add them all up, we'll get to 16 over 4, which is about $4. That is our expected yield, or what we are expecting to get. So what is our expected gain? So what are most players expected to get if they have to pay $5? Well, our expected gain is our yield minus our cost. Okay, so we have 4 minus 5, which is equal to -1, or minus $1. So most people are expected to lose $1 in this game. So unless if you would like to lose $1 or would like other people to lose $1, you would not recommend this game. Okay, you would not want to recommend this game because most of the time, the average of the time, you are losing money. So we would not want to recommend this game. All right, so now we're going to transition a little bit. We're going to move on. We're going to go to binomial experiments, okay? So binomial experiments, we're going to talk about success and failure. So when we talk about that, we have to think that we're only going to have two different outcomes in an experiment. So we're either going to get heads or we're not going to get heads. We're going to either get 6 or we're not going to get 6. Or we're going to get evens or we're not going to get evens. So that's what they're talking about here, success or failure. So you're going to get one result or the other. These trials must be independent of each other, and the probability of success, P, must be constant throughout the whole thing. So it's always going to be 1/2 chance to get heads, or it's always going to be 1/6 chance to get number 6. So we have the spinner right here at the bottom left. Would the spinning of the spinner below be considered a binomial experiment? If so, construct a spike diagram for the probability of distribution if we, let's say, if we spun it twice. So 2 trials. So if we had 2 trials, construct a spike diagram, and if not, explain why. So try that out a little bit, then we'll come back and talk. Okay, so I would say that yes, it is a binomial experiment. Okay, so success equals blue. So whenever we land on blue, we succeeded. Failure equals not blue. Okay, so whenever we don't land on blue, that is considered a failure. So if we want to construct a spike diagram, so if P of x equals 0, so we have no successes, so we landed on white twice, then that's equal to 2 choose 0 times 1/4 to the second times 0.75 to the 0. Okay? 2 choose 0 is just going to be 1, so we're going to have 1 times 1/4 to the second, which is 1/16. Okay? Now we're going to have P x choose 1, which is 2 choose 1, times 1/4 to the first times 0.75 to the first. All right, so if you multiply this out, it's going to be it's going to be 3/8. Okay, so now if we have a P of x to the 2, so I landed on blue twice, I succeeded twice, I have 2 choose 2, which is just going to be 1, multiplied by 1/4 to the 0 times 0.75 to the 2. So 2 choose 2 is just going to be 1. And then 0.75 to the second is going to be 9/16. Okay? And if you look at that, that equals out to 6/16. So if we add those all up, we're going to get 16 over 16. So if we make our spike diagram, so we have our, let's say we have 10/16 up here, we have 5/16. Okay, so here's where we choose none, and we just go up to 1/16. Here's where we choose 1. We got 1 of the blues, so we go up to 6/16. And here's where it's 2, and we go all the way up to 9/16. So that's how it would look if we had a trial of 2. Okay, so the binomial probability distribution, consider a binomial experiment in which P is the probability of success, and then 1 minus P is the probability of failure. And this makes sense because if you did P plus the probability of your failure, so if we did the probability of success and the failure add together, we should get 1. So 1 minus P should be our probability of failure. So if we have n number of trials, then the probability that there are r successes and n minus r failures is given by our equation right here. So we are always going to have our number of successes with our probability. So we're always going to have the number that we are going to succeed multiplied by the probability of succeeding. Okay? And then P to the x equals r is the binomial probability distribution function, which is given above. And our expected mean or outcome of the experiment is mu, which is equal to n times p. So the number of trials times by the probability of success. And if x is a random variable of a binomial experiment, then the parameter of a binomial experiment with the parameters of n and p, then we write x is distributed as b parentheses n p. So we read this as a symbol that kind of almost looks like a part of the about equal to sign is distributed as. Okay, so if we have 72% of union members are in favor of a certain change to their condition of employment, a random sample of 5 members is taken. The probability that 3 members are in favor of the change in condition, and then find the probability that at least 3 members are in favor of the change in condition. So we've kind of done this before. Why don't you guys try this out? And then we'll come back and we'll go over it. Okay. So the probability that 3 members are in favor. So R, which is equal to our successes, we have 3 members that are in favor. N, which is our number of trials, is equal to 5 because we're selecting 5 different members. P is equal to 0.72. That's our probability of success. And we'll just say F is our failure, which is 0.28. Okay? So we have our probability of x when x equals 3 is equal to 5 choose 3 times by 0.72 to the third times by 0.28 to the second. All right, so that's going to be the probability of our success and the probability of our failure. And if you calculate that out, you should get about 0.293 or 29.3%. Okay. Now, the next question asks the probability that at least 3 members are in favor of change. All right, so the probability that at least 3 members are in favor of the change. Well, we could either add up the probability of 3 are in favor, 4 and 5, or we could do 1 minus the probability of 0 are in favor, 1 are in favor, and 2 are in favor. So I would like to do the probability that 2, oops, I wrong second. That 2 or less are in favor of the change, and then I'll find whatever that is and do 1 minus that. Okay? So if you go to your calculator, we can do second variance. Do the binomial cumulative distribution function. Okay? We have 5 trials. Our probability for success is 0.72. Our probability for, and then we want to add up until we get to 2. All right? And we find that, and it's going to be 0.13764, so on. All right? So if we do 1 minus our answer, we'll get 0.8623. All right? And come back here. So our probability for success is 0.8623, or about 86.2%. Okay? It just makes it a little bit go faster if you're going to do 1 minus, and you're going to be able to use your calculator, because it just, otherwise you're going to have to add up all those probabilities. Okay? So C, what is the expected number of members in the sample that are in favor of the change? So if we look at this, this is going to be our mean value, or we're going to try to find mu here. Okay, so mu is going to equal to the number of people that we surveyed, or that they went, the number of trials, times by the probability. So if we got 5 people, we asked 5 people, and the probability that they were in favor was 0.72. That's going to equal to about 3.6 members. So that's how many members are going to be in favor of our change condition in their employment. Okay. So hope you learned a little bit about how to calculate the expectation of a random variable experiment, how to calculate the expected return from a game, and how to use binomial probability distributions to calculate the probabilities of a binomial experiment.